Okay, so I've got one more topic on applications of integrations that we're going to take a look at for Chapter 7. So we're going to skip to Section 7.4, and there's two topics we're going to look at in this section, and that's finding the length of a curve or arc length and finding the surface area when we make those rotations. And the videos here are going to start with a little bit of theory into where the formulas come from. Just try to follow along. If you're a little lost on how I'm getting the formulas, don't worry about it. I'm not going to ask you to do this on a test or anything. As long as you understand how the formulas work and get the setups for the integrals, that's the most important part for this section. I won't even make you memorize the formulas, but just kind of walk through these with me as we get to the main formulas. So we talk about the length of the curve. Think about like if you have a circle and you want to know the circumference of the circle, that would be the length around that entire circle. So that's basically what we mean. We're looking for the length. If I took a tape measure and I wanted to measure how long this is from point A to point B, what we could do, so the theory behind this here is we could think about zooming in and looking at a very, very, very tiny distance. I'm going to call it ds, and to the point where it's almost a straight line. And remember the Pythagorean theorem. So if ds is the little section I'm interested in finding the length of, well, I know dx is a small change in x and dy would be a small change in y. And based on the Pythagorean theorem, we could find ds, right? We would say ds squared, of course, is dx squared plus dy squared. So ds would be the square root of dx squared plus dy squared. And the idea is we want to think about not just that little section ds. Now, I've superimposed it in this picture so it doesn't look like such a little section, but it would be an infinitely small section. Well, we have an infinite number of those sections across the entire length. So if we wanted to get the entire length, we would add all of those little sections together. Well, that means we're back to the integral again, right? So we're integrating each of those little sections. And so the integral of the square root of dx squared plus dy squared is what we're interested in. What I did is I divided through here in the next step by dx squared. I'm using some algebra here, being a little loose with the rules here, but go with me for just a minute. Notice what I've done though. I've divided by dx squared under both of the terms that are being added, and at the same time I've multiplied by dx squared, which is how come I'm allowed to do that, right? As long as I divide and multiply by the same thing, it's like multiplying it by 1. Well, what is dx squared divided by dx squared? That's just going to be 1. So this turns into 1 plus dy squared divided by dx squared. And notice where this dx came from. Well, I had the square root of dx squared. Dx squared was under the radical, so the square root of dx squared is dx. So the rest of it stays under the radical. The dx goes on the outside. And of course, dy squared divided by dx squared, that's just the derivative squared. There's a lot more to this that we could get really into, but we're going to keep it simple, and this is what I want you to focus on. So the length of a curve, and it says Cartesian because later on we're going to talk about parametric later in the course, which is another form, but when we're working with regular old XY coordinate system, the length from point A to point B is given by the square root of 1 plus the derivative dy dx of the function squared with respect to x. So let's look at an example. Suppose I want to find the length of the curve negative x squared plus 9, so we know that's a parabola that opens down from 0 to 3. So the formula says I need to know the derivative of the function, which would be negative 2x. So we're going to do the integral from 0 to 3 of the square root of 1 plus the derivative squared. So that's 1 plus negative 2x squared, which is 1 plus 4x squared. Now, I want to point out this is actually not an integral you can do by hand at this point. We're going to get into more integration techniques when we get to Chapter 8. But for now, just take my word for it. That's the setup. And if we put it into Desmos or put it into our graphing calculator and ask the calculator to integrate, and that's what they did in the example. Don't worry about all that natural log stuff. Not a big deal. Just know that if we put it into a computer and have the computer calculate it, we'd get the value of 9.747. As long as you can get the setup here, that's what I'm most concerned with. In the real world, you would use technology to actually do the integration. The PowerPoint here gets into a way to check this. You don't have to write this down. They're just saying if we just looked at the curve of the rectangle, the length of that hypotenuse there, we would get, let's see, the square root of 90, which is about 9.49. Notice that that would be a little bit shorter than the arc length I had. So the arc length I had of 9.747 sounds about right if the hypotenuse drawn in red there for that triangle is 9.49. Okay, let's try another example. We've got the semicircle x squared plus y squared equals 1, and we want the arc length, let's say, from -1 to 1. So the first thing I'm going to do is I'm going to solve for y, so I move the x squared to the other side. So another way of expressing the semicircle would be y equals the square root of 1 minus x squared. Actually, that is the formula of just the semicircle. X squared plus y squared would be the entire circle. But all we want is the semicircle. So if we want the arc length from -1 to 1, I need the derivative of the semicircle formula right here. Well, think about taking the derivative now. You got to think differently. We're not doing an integral right now. We're doing a derivative that requires a chain rule. And if we went through and did the chain rule and plugged that into this arc length formula here, used a technology to help us, we would get an arc length of 3.14, which should make sense to you because the circumference of the entire circle would be 2 pi. So half of that would just be pi, which is this number right here. Okay, if we have an equation, it's easier to solve for x instead of solving for y. We can use the same thing. There's nothing special we have to do for arc length. We just use y instead of x. We change the variable. So for example, find the arc length of the function x equals y squared from y equals 0 to 3. So we basically want the length of this curve just going from 0 to 3 for the y values this time. So we're going to set it up, but notice instead of dy dx, I wrote this as dx dy, so it's the derivative of the function x with respect to y. So the derivative with respect to y, of course, is 2y. So again, if we put this into technology, we'd get a value of 9.747. All right, let's take a look at surface area. All right, so for surface area, the formula is a little bit more involved. And again, I'm just going to give you the background of where this comes from. You don't have to worry about reproducing this on a test or anything. I just want you to see. Surface area, remember, is from a three-dimensional figure. If you have a three-dimensional figure and you want to calculate the area of all the faces, that's your surface area. So if we take a curve and we rotate it, just like we were doing with volume, around, say, the x-axis, the surface area for this little band right here, so the area of the whole thing, will be given by 2 pi r ds, and that's because we're looking at the surface area of a cylinder again. Just like we were doing with volume, now we're looking at surface area. So it would be 2 pi r h, but h is the short little distance ds, just like it was when we did volume. So the total area given, let me show you what we've got here. So we're looking at the surface area of this cylinder, so it's 2 pi r. R, of course, is the y value where the function hits the curve, and ds, of course, is the arc length. Now, how do we get arc length? Well, that's what we did just a few minutes ago earlier in the PowerPoint. So the ds becomes the arc length formula we had just a few minutes ago. Let's put this all together. When we're going around the x-axis, here's what we're going to use. 2 pi, notice that's a constant multiple, so I moved it to the front, times the integral from a to b of the function f of x times the arc length, which was, remember, the square root of 1 plus f prime of x squared, dx. That was the formula we had earlier. If we're going around the y-axis, this formula just changes everything in terms of y. So we've got 2 pi times the integral of the function in terms of y times the arc length again in terms of y. Don't get too hung up on where these formulas are coming from. If that's a little fuzzy, it's not a problem at all, as long as you see how to apply the formulas when you have the picture. So let's look at some examples. So let's say we want the surface area when this line is rotated around the y-axis. So essentially, because it's a straight line, this is the surface area of a cone. And let's say the equation is given by the function y equals -4/3 x plus 4. So because we're going around the y-axis, I'm going to use this second version of the formula, which means I need to put everything in terms of y. So I'm going to solve the equation, first of all, for x, which means I've got x equals -3/4 y plus 3. That's the function in terms of y. I need the derivative. So notice I put dx dy here, but of course that's the same thing as just saying f prime of y, same idea. So the derivative of the function in terms of y would be what? That would be negative 3/4. So when you put it all together, we have 2 pi, which I can move to the front, of course, times the function in terms of y, times the square root of 1 plus negative, this should be negative, but it's going to be squared anyway, negative 3/4 squared in terms of y. And I don't want you to integrate that by hand. We're going to go ahead and use technology to do that. And I'll show you again how to integrate in your calculator, so make sure you bring those with you. Even though it's in terms of y, we can still put this in our calculator because it's going to treat that as a dummy variable anyway, but we get a surface area of 15 pi. From geometry, they're just reminding you, because this was a cone, we actually could use geometry to figure out the surface area of this cone, and we would get 15 pi. So there's a way to check our work. Don't have to do that every time. They're just showing you that the formula works. Let's try this one. The arc length, they want to find two things, the arc length and then the surface area found when this is revolved around the x-axis. So we've got the function y equals x squared minus 3x, and they want us to limit it to the interval x is 1 to 3. You're going to draw a picture before you do anything else. Make sure you make a sketch. Let's start with the arc length. So that's the formula we had previously. So it's the integral from 1 to 3 of the square root of 1 plus the derivative, 2x minus 3 squared in terms of x. Use the calculator to get that. We get a value of 3.4. Now for the surface area, we're going around the x-axis. So I'm going to use that first version. Look back at your notes of the formula. That first version of the surface area. So it's 2 pi times the integral from 1 to 3 of f of x, which is x squared minus 3x, the original function, times the square root of 1 plus the derivative squared. And you can't just put in that 3.4. You've got to actually put in the function again for the arc length. And then we're going to use technology to integrate that, and we get a value of 30.22. We're going to keep these pretty simple. We're going to just limit ourselves to either going around the x-axis or the y-axis. So as long as you have those functions and you draw a picture, you should be good to go every time.